Fascinating source material you've shared with us today. It looks like a collection of articles and notes, all about one of the universe's most, well, peculiar particles,
Uh,
the neutrino.
That's right. And the focus for this deep dive is really their strange behavior, or maybe the lack of behavior, when they meet these incredibly high energy, high density environments, like fusion reactions, whether that's deep inside a star or in one of the reactors we're trying to build.
Exactly. Your sources seem to really zero in on this puzzle.
hmm
Why do these particles just kind of sail through environments that are otherwise just packed with immense forces and energy? So our mission today is to unpack what your material reveals. Look at the fundamental properties that make neutrinos act like these ghosts, figure out where they come from in fusion, how they interact, or, well, mostly don't interact, and what happens to them as they, travel out from the core.
Yep. We're aiming to pull out the really essential insights from the sources you've got there, just to give you a clear picture of this really counterintuitive stuff.
Okay, let's unpack this then. The core mystery your sources jump on right away is that the overwhelming majority of neutrinos pass through fusion plasma, completely unimpeded. I mean, this is fusion we're talking about. Everything else is smashing together, reacting. Why are these tiny particles just, ignored?
It really boils down to their fundamental nature, just as the sources explain. There are basically two key properties that give them this invisibility cloak, you could say. First, they have an extremely small interaction cross-section.
Okay, interaction cross-section.
Yeah.
That's basically the chance a particle will actually hit or interact with another one, like how big a target it seems to be.
Exactly that. And for neutrinos, that target size is just minuscule. That's because they mainly interact through the weak nuclear force.
The weak force, okay, the name kind of gives it away, but how much weaker are we talking? Compared to, say, the electromagnetic force or the strong force that's really running the show in fusion.
Oh, orders and orders of magnitude weaker. Your sources are clear on this. The weak force isn't just less powerful, its range is also incredibly short. Very, very short. So that combination just makes the probability of a neutrino actually, hitting something or getting close enough to interact via that weak force with a proton or neutron or electron in the plasma. Well, it's extraordinarily low, really low.
Got it. So reason one, interacting via the weak force is almost impossible in this situation. What's the second big reason the material points to?
That they have no electric charge, they're electrically neutral.
And in a fusion environment, which is full of this super hot plasma, basically a soup of charged particles, ions, and electrons, why does being neutral matter so much?
Well, because that plasma, that soup of charged particles, it's being held together and controlled by incredibly powerful magnetic fields. Think about tokamaks, stellarators. Since neutrinos don't have any charge, they are just completely unaffected by those fields. They don't feel any push or pull. They don't follow those swirling paths the plasma particles are forced into. They ignore the magnets completely.
Huh. So they aren't steered or trapped by the magnetic fields that are designed to hold the plasma, and their chance of actually hitting something via the weak force is tiny. That's kind of the 1-2 punch then. Explains why they just fly straight through.
That's exactly it. They are, essentially immune to the two forces that really dominate that plasma environment. They ignore the strong electromagnetic forces, and the weak force interaction probability is just too low to matter for most of them.
Okay, so they're passing through. But where do these ghostly particles actually get made in the first place?
Yeah.
Sources talk about this, right? Is it the same story in a star versus an experimental reactor here on Earth?
Yeah, and that's where your sources draw a really important contrast. It's quite different. In stellar fusion, like in our sun, neutrinos are a direct and really abundant byproduct of the main nuclear reactions happening in the core.
You mean in the process where hydrogen turns into helium, that kind of thing?
Precisely. The main ones are the proton-proton chain, the PEEP chain, and also the CNO cycle. These reactions involve protons changing into neutrons, right? And that change often spits out an electron neutrino. The sources give that classic example from the first step of the PEEP chain. Two protons fuse, they make deuterium, a positron, and importantly, an electron neutrino. So the sun is just, an absolute torrent of these electron neutrinos pouring out constantly.
Okay, so stars are basically neutrino factories because of their fusion. What about our attempts to make fusion happen down here?
Well, that's where it's different, according to the sources. Current designs and the ones we expect in the near future, mainly using deuterium-tritium DT fuels, or maybe deuterium DD, they do not directly produce neutrinos as the main product of the energy-releasing reaction.
Right, I remember D plus T fusion gives you helium and a neutron. No neutrino in that equation.
Correct. And the D plus D reactions, they either give you helium-3 and a neutron, or tritium and a proton. Again, no neutrino coming directly from that primary fusion event itself.
But wait, the sources do mention some neutrinos are produced in reactors. How does that happen then?
Yes, but it's mainly through secondary reactions, or more typically from radioactive decays happening alongside the fusion. The main example cited is the decay of radioactive stuff in the reactor, particularly the tritium fuel. Tritium undergoes beta decay, and that decay produces electron antineutrinos. But see, that's a radioactive decay process. It's separate from the main fusion reaction that's generating the power, and the total number of neutrinos is way, way lower compared to a star.
And they even touch on those future ideas, like aneutronic fusion.
They do, briefly. Concepts like proton-boron 11 fusion. The whole point there is to minimize neutron production. And as your sources note, these ideas would also have like negligible neutrino output compared to stars. So yeah, the origin story for fusion neutrinos really depends. Big difference between a star and a lab experiment.
That difference is really key, isn't it? Okay, so whether they're born right in the stellar core or as a kind of side effect in a reactor, let's get back to their amazing journey through that plasma, that incredibly dense, hot stuff. How do they navigate something that intense without interacting?
Well, it comes right back to that incredibly low probability of interaction we talked about, even inside something as dense as the sun's core or a fusion plasma. The sources really emphasize that neutrino's mean free path, that's the average distance it travels before it actually does interact with something, is just astronomical.
Astronomical how? Like, give us a sense of scale here. What do the sources say?
Your sources give a comparison that's, well, it's pretty mind-blowing, actually. They state that the mean free path of a typical neutrino is vastly larger than the size of any fusion reactor we could build. It's even vastly larger than the entire core of the sun itself.
Wow. So even inside the sun's core, most neutrinos just fly straight out without hitting anything. They travel further than the size of the core before maybe interacting.
It's even more extreme. To really hammer the point home, the specific analogy your sources use is that a typical solar neutrino could travel through light years of solid lead before it has a decent chance of interacting with a single atom.
Light years of lead. Okay, that really drives home how non-interactive they are. Just wow. But
Okay.
your sources do briefly mention that if an interaction does rarely happen, what kind of interaction is it?
Yes, in those super rare moments, it's the weak force again. There are a couple of types. There's neutral current, or NC, scattering. That's where the neutrino sort of bumps off an electron or a nucleus. It exchanges a neutral particle, a Z boson, and scatters off. But the neutrino stays the same flavor electron, muon, or tau.
Okay, so it changes direction maybe, but it's still the same kind of neutrino.
Right. Then there's charged current, or CC, scattering. That's less common. It requires, for example, an electron neutrino with enough energy. It can interact with, say, a neutron, turn it into a proton, and the neutrino itself transforms into an electron, so the flavor changes and charge is exchanged.
But the really crucial consequence, like your sources point out, is that because these interactions are so incredibly rare, they result in
negligible energy deposition, basically zero heating. The neutrinos just carry their energy straight out of the fusion zone. They don't dump it into the plasma and heat it up in any significant way. And this fundamental property, this is why detecting solar neutrinos here on Earth became such a vital tool for understanding the sun. They arrive here carrying basically undistorted information directly from the sun's nuclear furnace, having barely noticed the millions of miles of dense solar material they just passed through.
And just to reiterate, those powerful magnetic fields, they just don't care about them.
Exactly. No electric charge means totally immune to the magnetic confinement field. Doesn't matter how strong they are.
Did the sources mention anything about, like, collective effects? Do neutrinos ever interact with the plasma as a group?
They do add that nuance, yeah. But mainly just to say it's not relevant for what we're talking about, not for stars like our sun or current reactors. These collective interactions where maybe a really high density of neutrinos might start behaving differently. That's theoretical stuff for extremely dense situations, like inside a collapsing supernova core, or maybe the very early universe. Conditions that are just worlds away from a normal star or a fusion device.
Okay, so for our purposes, stars and the fusion reactors, we know they're pretty much individual non-interacting ghosts just passing through.
That's the picture, yes.
All right, so they've made it through the fusion core. They're carrying their energy away. What happens next as they travel, especially over vast distances? Your sources bring up this really interesting idea of neutrino oscillations.
Ah, yes, this is where things get even weirder in a quantum mechanical way. Neutrino oscillation. It's a proven phenomenon where neutrinos actually change between their different fundamental types, their flavors. They can start as an electron neutrino, and later on you might detect it as a muon neutrino or a tau neutrino. They morph as they travel.
Like a particle playing dress-up while it flies.
Sort of, yeah. And how this plays out really depends on the journey, especially if they travel through matter. Your sources break this down nicely. In stars, like our sun, you get electron neutrinos born right in the core from those fusion reactions we discussed. But as they fly outwards through all that dense solar material, they start oscillating. And the sources specifically mention something called the Mikheyev-Smirnov-Wolfenstein effect, usually just called the MSW effect. This effect describes how traveling through matter, specifically, actually enhances these flavor changes. It makes the oscillations happen more readily or changes the pattern.
Hold on, is this the solution to that old puzzle? The solar neutrino problem, where early experiments only found about a third of the electron neutrinos they expected from the sun.
Exactly. That was one of the biggest pieces of evidence confirming neutrino oscillation and the MSW effect. It wasn't that the sun was making fewer neutrinos. It was that by the time those electron neutrinos reached detectors on Earth after traveling through the sun's dense interior and then across space, a large chunk of them had already changed into muon or tau neutrinos, which those early experiments couldn't detect. So the journey through the star's own matter fundamentally changed their flavor mix before they even got out.
Wow. So the matter they travel through, especially over long distances, has a profound impact on what flavor they are when they arrive. What about inside our fusion reactors on Earth? Does this happen there too?
Well, your sources are pretty clear on this. The distances involved inside a man-made reactor are just way too short for significant oscillations to occur before the neutrinos are long gone. If you produce, say, electron antineutrinos from tritium decay, they're overwhelmingly still going to be electron antineutrinos when they exit the building. The MSW effect, or even vacuum oscillations, just don't have enough time or distance to make a noticeable difference over those sorts of scales.
Got it. So oscillations are super important for understanding neutrinos from stars that travel light years, but basically a non-issue for the ones produced inside a relatively tiny reactor chamber.
That's the key distinction the material makes, yes.
All right, so we followed the neutrino from its birth, through its near-invisible passage through the plasma, and out on its journey, where it might even change its identity. Let's wrap this up. What are the main takeaways your sources really want us to get?
Yeah, the sources kind of bring it all together nicely. First, neutrinos are created in some fusion processes, way more as a direct primary product in stars. Much less so, and often indirectly, in the types of fusion reactors we're currently working with.
And the absolutely dominant theme is their ability to just pass straight through the fusion plasma, almost completely ignored.
Which, again, comes down to that tiny interaction cross-section because they use the weak force and, crucially, the fact they have zero electric charge.
Meaning those huge magnetic fields used to control the plasma, they don't interact with neutrinos at all.
Not a bit. And while they do oscillate between flavors as they travel, especially over cosmic distances through matter like the sun, where that MSW effect really kicks in, that whole phenomenon is pretty much negligible over the short distances inside terrestrial fusion devices.
So the overall picture the sources paint is that the fusion plasma itself, no matter how hot or dense, is almost entirely transparent to the neutrinos passing through it.
Absolutely. They really are these ghostly messengers. They carry information straight from the heart of these incredibly energetic events, these fusion cores. Yet they travel through that intense environment almost completely unperturbed by the chaos and forces all around them.
That's a really powerful image when you think about it.
It really highlights how unique these particles are. You have this environment defined by immense forces, incredible heat and density, and these things just slip right through the cracks, barely registering any of it.
So you've taken us on a deep dive into why neutrinos are such unique particles. They act like messengers from the most energetic places we know of, yet they barely interact with the energy they witness.
And getting a handle on these fundamental properties, the weak interaction, being neutral, the oscillations, it's absolutely key to understanding why they play the role they do, or perhaps the non-role they play, in fusion energy systems, both the natural ones and the ones we hope to build.
It really makes you think, doesn't it?
Yeah.
While we wrestle with containing and studying the intense forces and fields of fusion, trying to understand it, these almost undetectable, practically non-interacting ghostly messengers just scream right through everything. And they carry perhaps the most direct, unaltered information about the reactions happening right at the very core. It's like a window into a world we can barely touch with anything else.
Yeah, what does it really mean to get your information from something that's so completely detached from the incredibly violent and energetic place it just came from?
That is a fascinating thought to leave you with as you ponder the sources you shared. Thanks for joining us for this deep dive.